Probably we can start. Good evening. Hello, everyone. My name is Werther Guigi Nissim, and first of all, I would like to thank all the professors here who invite me to hold this seminar today. I'm here thanks to Erasmus Plus project, which allows teachers from different universities within the EU to exchange, and basically provide seminars and lectures within different universities. It's a very, to me, it's going to be very challenging, but also very exciting to be talking today here, because it's one of the first time that I have to show my research to let's say, plant scientists, because I think most of you are from a background in architecture, so landscape architecture, actually. But I come from another background, so I try to organize my presentation in a way that is not very too much boring for you. I mean, with a lot of technical stuffs and mechanisms and things like that. But the topic I'm working is phytomanagement, and then we will see what it means. And bringing here some practical experience of application, of course, from the Mediterranean region where I'm from, because I'm from Italy, and also in other temperate climates which are similar to what is here in Czech Republic, although I made a lot of experience in North America, actually in Canada. So just for introducing a little bit my background, at the moment I have two main, let's say, jobs. I'm actually a professor, contractor professor in applied botany at the Polytechnic of Milan. And that's why I'm here, because I'm applying as a professor at the Politecnico for this program. But actually, my main job is an assistant professor at the Department of Biotechnology and Biosciences at the University of Milan in Italy. And as you see, my background, my education is more in forestry sciences and agriculture. So what I'm going to talk, of course, is plants. And actually, my research goes around this topic, which is phytoremediation, analyzing the technology, so the reclamation of polluted site through plants at different scale, at different levels. I'm moving from the small level of the plants, so how the plants react to a contaminated and polluted environment by analyzing what we called abiotic stresses, like the presence of heavy metals in the soil, but not just that, but also water logging, drought, and so on. Then I investigate a lot the aspects related to the management of phytoremediation. I mean, using plants as a phytotechnology is not just planting, but it's also managing the plantation, the plants, in a way that you can get, the final results of cleaning up soils and so on. So I'm very interested in which are the technologies and the strategies to enhance the process through managing the stands. So harvesting the plants, tending the plants, fertilizing, and so on. So everything in order to get the best results in terms of the pollution, okay? And Also, I'm very much into the evaluation of the overall process by analyzing the actual working potential of different technologies. Especially here, I underline two technologies that I'm going to show you, which are phytoextraction and phytometabolism. And then we go. And last aspect, which now is becoming very popular amongst scientists in this area, is the assessment of ecological services related to phytoremediation. And I'm going to talk a little bit more of this aspect in the next seminar on Thursday. So when I talk about phytoremediation, I think it's becoming popular technology, but then a definition is always very important to provide. For phytoremediation, I intend a phytotechnology, a technology which includes three main strategies, which are the degradation, the removal or the stabilization of some environmental contaminants by the plants, of course, and also I would add by microorganisms living within the root zone, what we call the rhizosphere, or within the plant, the endosphere. One may ask, why do we need this technology and this approach to fix environmental issues? I'm very sad that the first one is because, in general, phytotechnologies are less expensive in terms of money. It's very sad to be here and talking about the same, with the same approach of talking about money, but it's very important that our techniques, our technology are not competitive to most conventional reclamation techniques. And actually, phytoremediation is very cheaper compared to that. But of course, the big maybe advantage is in terms of providing biodiversity, because we are working with plants, living organisms. So we are most of the time bringing back life into very complex and contaminated area where biodiversity is very low. So by providing new plants, we enhance the overall biodiversity of the area. We think that our approach is also aesthetically more pleasant than most technological, let's say, engineeristic approaches, decontamination techniques. And that's why when you are talking to people about project of phytoremediation, they are very happy. So there is a kind of high social acceptance, okay, because they are very willing, or they prefer to see their land covered in green plants rather than, heavy machineries and so on. And in fact, some phytoremediation approaches here on the bottom are a picture that I took in Canada, where I worked for several years. Of course, using some plants is also good looking. I'm not trying to convince you about the aesthetics, but I think that the green effect is always something nicer than digging a hole and that's it. But unfortunately, the techniques are not ready yet for actual application. It still shows some drawbacks, some weakness point. First of all, when the sites are too polluted, plants cannot withstand, cannot survive. I mean, sometimes people call us and say, okay, I have a polluted site here, can you come with your plants and do some? And then we realize that the sites are completely a mess and too polluted for the plant to withstand. Plants are living organisms, and they have thresholds over which, I mean, they cannot survive. So, of course, the technology is not suitable in these cases. So we must put the plants where they are able, at least, to grow. Another issue, important issue and problem that actually we as a scientists try to kind of overcome is that in some cases the technology takes a lot of time to be working, which may sound strange to me, not because, I mean, a living organism into a very complex and polluted site can respond by decreasing the rate of growth. Okay, nobody wants to be in touch with toxicants and dangerous elements. Not even the strongest plant. Oh, thank you very much. But this is a very big issue and very big problem for people operating in the sector, because when we are competing with commercial technologies, they always say, oh, how long will it take for my field to be, you know, cleaned up with your plants? The answer is not easy to be given. Depends on the pollutants, depends on the plant, depends on many things. So this, of course, is gonna take years. So for some pollutants, decades, or, you know, even centuries, which may look very, you know, a very long time lifespan, time span, but in fact is not. I mean, sometimes may not be such a long time. But anyway, we are, as a scientist, plant scientist actually, we are working a lot to remove at least the second point. I mean, trying to make this period shorter by using, for instance, the right plants, you know, in the same, in the right for the right pollutants. We are trying to select new species. We are trying to manage the plantation and plants in general in a way that they are more effective in removing pollutants, and so on. In general, if you read books and publication, the classification of phytoremediation is very complex and always changing. I prefer to make it simple in dividing the technology into 4 main families. The techniques that are aimed at removing the pollutants, like phytoextraction, for example, where, as you see here, the plant is able to take up a specific pollutant from the soil or from the water, and then through the roots, of course, and then to store it within the biomass. Okay, this is first family of phytoremediation. The second one is based on plants, and I would say the microorganisms which are able to degrade the contaminant. So the contaminants is taken up by the roots system, and normally is broken down into less toxic compounds. A third family is the stabilization, where plants are not removing anything, are not degrading anything, but they are able to stop, to block the contaminant in the soil. And then we'll see how. But the big advantage is that even though the contaminants are not removed off the site, they won't move. They will stay in the place where they are. And the last one, so the fourth categories is when plants are able to use directly the contaminants within their metabolism. So it's like if the plants are eating, okay, the pollutant as well. So just to show you some principle of each one family, the phytoextraction, as I said, is when the pollutant is taken up by the plant and stored within the biomass. So the technology works when you are able to harvest the biomass, which contains a lot of pollutants in the biomass, and then you can remove the pollutants from the site. This technology is very suitable for specific environmental contaminants, in particular what we call the trace elements, metalloids and metals, like you see here, arsenic, cadmium, chromium, copper, nickel, lead, zinc, and so on and so forth. Basically, when you hear people talking about phytoextraction, the technology is relying on two groups of species, of plants, of course, which are either hyperaccumulators or fast-growing species. The first family is a family of metallophytes, which are plants adapted to live on soils which contain a lot of heavy metals inside. And so they can withstand a high concentration of metal within their tissues. The second family, the fast-growing plants, are plants that are not able to concentrate heavy metal within their biomass, but because they are very productive in terms of, ponderal body, they grow a lot. In the end, the result is almost the same. Hyperaccumulator plants are very small. Fast-growing species are very huge, big, okay? So in the end, even though the first family is able to concentrate a lot of metals within their biomass, in the end, the result is almost the same. The approach of phytoextraction is very challenging still. And then you will see, I will show you some project I worked in with that. Because the strategy works very well when the environmental condition, especially in terms of type of soil, are met. Otherwise, most of elements, toxic and this kind of trace element, heavy metals, are not very available for the plant, and the technology doesn't actually work. Takes time, so can be very slow process. Here, for example, you see some pictures of hyperaccumulator plants like Nocea cerulescens and Sedum alfredi here on your left, and fast-growing species, which is a willow, Salix miabiana. So two different approaches for the same type of contaminant, heavy metals. The second strategy, as I said, is a degradation, and that strategy applies especially to organic pollutants like hydrocarbons and other dangerous organic pollutants. And it works very well because the plants, and oftentimes also the microorganisms living within the rhizosphere, are breaking down the pollutant into something less toxic. The species that are used are different. Normally, there are two groups of species that are very effective for the degradation of specific hydrocarbons. For example, poplar are very effective, but also species like alfalfa and white clover for different reasons, but they look very high performing for the degradation of these compounds. The striking thing is that unless what we saw for phyto extraction, so it takes a long. Normally, when you find the right species and you choose the right species here, the process can be very fast. In a couple of years, choosing the right species can almost, you can get almost a clean soil in a very short time. Of course, there are organic contaminants. They are not targetable with that because they are very resistant. But some are very easily destroyed. As I said, phytostabilization is most an indirect strategy to prevent the spreading of the contaminant all around the environment. So we use plants that basically produce through the roots substances like some molecule that transform, that bind actually the contaminant and transform it into something which is less mobile, so very stable, in a way that he won't move and he won't spread out the environment. It's a strategy of, let's say, avoiding the dispersion of contamination throughout the environment. And last, as I said, the phytomanagement, it's the best solution because it's when the plants are able to use the pollutants for their own metabolism, which is something very common when we are dealing with some particular environmental pollutants like nitrogen and phosphorus. You may have heard about the problem of eutrophication, I think, which is when huge amount of nitrogen and phosphorus are released into the water bodies, and you know they are actually producing an overproduction of algae and so something like this that make our rivers and lake slowly dying. If we use specific plants to remove that, of course, nitrogen and phosphorus are, yes, environmental pollutants, but also nutrients for the plant. So in this case, if we choose the right plants, there are normally fast-growing plants, very, very with very high requirements in terms of nitrogen and phosphorus. We are able to filter, this kind of waters and obtaining very good results. Okay, so once we introduce this technology, the idea of this seminar is to just provide you some example of some applications, actual application, although it's research, it's not, it's not a technology that can be sold. So these are results from research project. But yet, the idea was to provide you with some example of application at a real field scale, not in laboratory, not in a greenhouse. And I chose to show you two projects of phytoextraction and phytometabolism. The first two case studies were actually in my country, in Italy, and the last two in Canada. So also in in a way that you can compare a little bit different environments because maybe interesting. So the first project is a project that was run 5 years ago, I think, in the very south of Italy, in the city of Taranto, in a Puglia region, and was a military site polluted moderately, I would say, by 3 trace elements, heavy metals, copper, lead, and zinc. I don't know here in the Czech Republic, but in Italy we have special legislation which protect the secret within what happened in the military sites. So the law that normally applies to normal environment in military sites are not the same. And in fact, the environmental standards for such a sites are very low. So basically, now there are a lot of hotspots contaminated in military bases. And in fact, when we went to the site and start sampling, what we found was a huge deposit of different waste. And it's very fun because sometimes when we are talking to people about plants that can be used for land reclamation, they think that they can plant trees over metal objects like batteries or whatever, and the plant is gonna make a miracle. Not at all. I mean, nobody's going to decontaminate a soil where there are waste materials everywhere. So the first thing that we have to do when we go to such sites is to physically remove some some important materials. Otherwise, the technology won't work. Also, another aspect that we have to take into account is the preparation. I mean, now there is this kind of wrong picture that you plant a tree and the game is over. No, we must try to create a good environmental condition for the plant to establish. Okay, otherwise the technology won't work. So it's very important to treat your site as an agricultural, land, as you were farming something like, wheat or corn or whatever. So it's important to plow, for example, the land and to provide fertilizer. For instance, here we have to install also an irrigation systems because we are far in the south where there is some drought. Problems related to the scarce rainfall. Then, of course, you have to sample your soil because it's important to have a time zero, a point zero, to compare your results with. And then the next step is, of course, choosing the species. As I said, I've been working mostly with fast-growing species. So here, for example, willows and poplar and industrial hemp. That is not the one that we smoke, but it's similar. Are fast-growing species, and alfalfa was chosen for other reasons because we also were interested in assessing the nitrogen fixation process during the remediation, and alfalfa is a nitrogen fixated species. Sorry, and basically, okay, this is just an idea of the contamination level within the site. And here you see two values, for example, for the concentration of copper, the total pool, which is represented by the total net content within the soil, and then the extractable fraction, which is the fraction of the total pool which is available for the plant to be taken up. it's important because the only thing the plant can do is work on this part. And then for a kind of equilibrium, as long as this part is being transferred to the plant, that form goes into this one. So there is a kind of mechanism, but it's very important to look at, you know, the scale of concentration. Here we are around 250 milligram per kilos, and that available fraction is very low in this case. The same for other metal, and you see also the distribution of the contamination is not very even. It's very uneven actually, and so sometimes it's not easy to address the overall problem by choosing, for example, one species, because probably you need a couple of different species to be more tolerant in that corner compared to this part and so on. But the same is also for other, you know, pollutants that we found. Here as the steps that we use to evaluate our technology, our approach. So the first thing that we have to do at the end of every year is to measure the biomass yield, how many kilos of, you know, biomass has been produced by different plants. And this is very easy. You just go, cut the plants and weigh it. So of course you have to probably express your yield in terms of dry matter. So you have to dry out your sample. And then, of course, you want to know the concentration of trace elements within the biomass. So you have to mineralize the biomass. So what we say, we digest the biomass in a way that we can extract the components, the mineral components within the biomass, and then analyze it for each, let's say, organ, leaves, stems, and roots. And then, of course, it's very easy. At that point, you just multiply the concentration of the element for the biomass produced, and you have what we called trace element accumulation, which is actually the phyto extraction. Okay, how much element has been removed and stored within the leaves and the stem in 1 year. And then what you do, of course, the last thing that you must do is sampling the soil once again at the end of the season, and to relate the concentration that you find to what you found at the beginning before starting, okay? And here, for example, I show you some results here. Here, for example, is the extraction of lead by different species in 2 years. The first and second year, and as you see, here you are just to look at two things. The first one is that there are differences between species in terms of phyto extraction potential. For example, here on average, hemp is the best performing species with almost 35 grams per hectare per year of lead extracted. And it's very surprising that it's not very much. 35 grams is very, I mean, 1 hectare, do you know how many square meters is 1 hectare? Is 10,000 square meters. So it's not a lot. But what is very surprising is that when you skip to another pollutant, for example here copper, the species changed because, for instance, here poplar is the best performing species, but also the amount of copper extracted every year increased. You see, here we are almost about 2 100 grams per hectare. And then if you go ahead, for example, here for zinc, you may extract up to 5 kilos of metal per hectare per year, which is, I mean, it's an important amount. Nothing surprised, because it's just that this happens because unless lead, which is an element, is not used by the plant, copper and zinc are micronutrients. So there is this kind of affinity between the plants and the pollutants, which may explain why we got such an interesting result. However, at the end of the second year, when we sampled the soil again, what we found was that, of course, there was a decrease, a general decrease in the concentration of the metal within the soil. Depends on the metal, depends on the plant used. But unfortunately, the only significant difference in terms of statistics, statistically speaking, were the colored one. You see the blue, the green, and the red, which are the concentration of the extractable part of the metal, and not the overall, concentration. This table means that in 2 years, the technology basically didn't work, because the Italian legislation and the limits are made on the total concentration, So in 2 years, we were able to decrease just the available fractions, which is good, because it means that probably in the next couple of years, also the total would decrease. But, it's not very fast. In fact, 2 years, you got almost nothing. Second case studies, again, here it's another military site here in the north, next to Genova, this is in La Spezia. Another military site, in this case, contamination is slightly different, because we also have antimonium with copper and lead and zinc. Here we also had some physical barrier and constraints, because that polluted soil was protected, polluted area was protected by a plastic layer, which couldn't, was there because previously the area was closed up and was not accessible, and we had this kind of heavy thick layer of plastic, and we didn't know what to do. Finally, we chose to operate with 3 species, fast-growing species. We added eucalyptus because it's very suitable for growing fast in Mediterranean climates. And we decided, here, to basically dig holes with this kind of instruments and use them to plant our trees. Here's the material that we use. For poplar willows, basically we use wood cuttings. It's very easy because they are very easy to propagate with that. For eucalyptus, plantlets, so plants of 2 years old plants. And then again, we have to provide fertilizers and so on. And luckily, after 1 month, all the plants were very happy, or looked very happy. See here, poplar. They grow very fast. That's why, we are interested. In a few months later, they were kind of small forest. We were very interested in following, as I say, the physiology of the plant, because we wanted to know why they are responding so well to such a high pollution. So here, for example, we are measuring the photosynthesis, which for the plants is the equivalent that for us for the temperature. We measure the photosynthesis rates as to say to tell whether or not the plant is doing well. And in the end, of course, we also sampled with the same philosophy, okay, of checking what's going on within the site. And what we found was that, of course, some spot of the area was very polluted. You see here how the size of the plants are related, inversely related to the contamination of the soil. For example, here you have the copper concentration within the ground, the soil, and the size of the plants. And here you can see my colleagues standing just beside the plants. They are kind of yellowish because they are suffering a lot by the high concentration in copper. However, again, there are some species that looked more. Sorry, the percentage is not supposed to be there. Anyway, this is the concentration of the metal within the plants, and here the phytoextraction rate. Sorry, we changed the computer, and then the formatting is not perfect. But anyway, this is what is the grams per hectare per years, and here also you may see the difference between species in terms of extraction. For example, poplar provided very high extraction rate for cadmium and zinc, whereas eucalyptus was very performing for copper and antimonium. So the preliminary conclusion related to these two case studies were that, of course, in most cases, the plants react very well to this type of contaminations. It's important when we want to adopt this strategy, phytoextraction, to match the right species, as you see, with the right contaminant. In this case, poplar provided very good results for cadmium and zinc phytoextraction, whereas eucalyptus promising for copper and antimony. Of course, I have to say that this is just my experience. I mean, you can go online and read a lot, literature about phytoextractions. There are research groups all over the world working with different group of species. As I said, I'm not working for the moment with hyperaccumulators because although they are very performing in terms of extraction, they are very, very hard to manage because they are very short, they are very small, and it's very hard to go and harvest their biomass. So as I said, this is a phytotechnology, so this is not just plants, but it's also managing the plants in order to get the result. But of course, the list of species which are suitable for phytoextraction is getting longer and longer and longer. And you go now. The research started in our, let's say, Western countries, North America, Northern Europe, and so on. And now it's spreading all over the world. So new species, for instance, for the Far Asia, are adding to the list, and now it's a technology which is under assessment also in other environments, like in the tropics, where of course there are different species. The key is stay within the soil. So the plant is not going to take up a lot of phosphorus from the system. So you have to be careful when your wastewater is very rich in phosphorus, because in a year you can have an accumulation and then some problems. So phosphorus is less easy to treat, but yet still interesting. Some picture about of the sites here. You see the greener color here of the plots is because we were supplying nitrogen, and nitrogen is the precursor form the chlorophyll. So you add nitrogen, you have greener plants. Here's some pictures within the filter. Okay, it's like a field, you know, very straight and very dense biomass. This is the filter after harvesting the biomass, because willows are able to resprout without having to plant. And again, I mean, you cut the plant, and by new buds, they are able to sprout and to grow new stems and leaves in the spring. This is the biomass that we produce using different treatments, and which was sometimes very high. And this is a moment where we harvest the biomass to be used for heating the school. And it's very interesting because to notice that we are trying to create, in this case, the systems that are very easy to manage with common machineries, tractor, and so on. That's why we need straight lines, straight rows, you know, and very intense plantation like this. These are the main conclusion of the project, and so of course we need more long-term assessment for checking, especially the dynamics of concerning the phosphorus. But otherwise, the project was very successful. Overall remarks on the technology, just to conclude, is that I would say phytoremediation is a suitable green option to address specific environmental pollutants. Otherwise, the performance up to now are very variable and depends much on the type of pollution. As you see, heavy metals are less targetable, less easy to be addressed with technology than other elements, like, for instance, phosphorus and much more nitrogen. And so I would say that taking into account this small picture I gave you, I would say that phytometabolism is still one of the best choice that you have, and something that you probably can adopt right away now without any risk. Phytoextraction is still under, let's say, construction, because we still have to fix some problem. Also, it's very interesting to underline, to highlight the fact that scientists today are also concerned about other aspects that up to now were not considered. For instance, the choice of the shape or the mix of species that can be used is continuously changing. As I'll show you, we began with very straight design with one or two or few species, because it was easy for us to understand the mechanism behind. Now the time has come for more complexity and for taking into account different types of approaches. For instance, using also natural plants that spontaneously establish on contaminated sites, although not all are suitable for phytoremediation. Anyway, the tendency now is really to work for creating patches, okay, of vegetation which are made by the best suitable species, probably mixing some of them like hyperaccumulators with fast-growing species. So creating complexity, which also mean creating something more stable from an ecological viewpoint, enhancing biodiversity and so on. That's it. I think, well, I made it short, I made it very light. Of course, if should anybody have questions or curiosity, I'm very willing to respond to your email. If anybody will visit my country, I have the chance here to have a student who attend my course in Milan. I'm so happy. And so I thank you very much for being here, and I'm here if you need some curiosity, some questions. Thank you very much.